Smallpox. Smallpox is the only human disease we have ever completely wiped out. It was officially ended in 1980 after a huge worldwide vaccination campaign. The virus killed around 300 million people in the 1900s alone, with about 30% of infected people dying. People who survived were often left blind or with terrible scars all over their bodies. It was a horrible disease that humans fought against for hundreds of years. And then we won. The last person to naturally catch it was in 1977 in Somalia. By 1980, the World Health Organization said smallpox was completely gone from nature. So why does smallpox still exist? Because we kept it. After we got rid of it, the WHO told all countries to destroy their smallpox samples or send them to two special maximum security buildings: the Centers for Disease Control and Prevention, CDC, in Atlanta, Georgia, and the State Research Center of Virology and Biotechnology, Vector, in Koltsovo, Russia. These are the only two places on Earth officially allowed to store live smallpox virus. The reason for keeping smallpox is research. Scientists say they need samples to make better vaccines, to study the virus in case it comes back, and to create treatments in case someone uses it as a weapon. But many experts believe the dangers are much greater than the benefits. The WHO has talked many times about destroying all remaining samples, but the US and Russia have always said no to complete destruction. Here's what makes smallpox so dangerous if it got out. No one under the age of 45 has been vaccinated anymore. Regular smallpox vaccination stopped in the 1970s once we got rid of it. This means most people in the world have zero protection. If smallpox escaped from a lab or was deliberately released, it would spread through a completely unprotected population. The virus spreads very easily through tiny drops when people breathe and through direct contact. An infected person can give the virus to others before they even show symptoms, meaning it could spread around the world before anyone realized what was happening. Modern airplane travel would let smallpox reach every continent within days. Computer predictions suggest that a smallpox release could infect hundreds of millions of people, killing 30% of them, possibly 100 million deaths or more. The security around smallpox storage is supposed to be perfect. Both buildings are BSL-4, biosafety level 4, the highest security level. Scientists work in special suits with their own air supply. Multiple safety barriers exist. Entry is severely limited. Samples are carefully tracked. But accidents happen. In 2014, FDA workers cleaning out an old storage room at a CDC building in Maryland found 6 bottles of smallpox in a cardboard box. The bottles had been sitting there, forgotten, for decades. They were in an area that wasn't even meant for storing dangerous germs. The bottles were intact, and the virus was still alive. If someone had accidentally broken a bottle, smallpox could have been released into an uncontrolled area. In 2021, a lab worker at a Merck building in Pennsylvania found frozen bottles labeled smallpox in a freezer. The FBI and CDC were called. The bottles were tested and fortunately did not contain actual smallpox. They contained vaccinia virus used in smallpox vaccines. But the incident showed that labs don't always know what's in storage, and dangerous germs can be mislabeled or forgotten. Having smallpox in labs creates other dangers. What if a bad scientist stole a sample? What if Russian or American security failed and the virus was taken? What if a building was damaged by a natural disaster or war? What if a worker was bribed or forced? Smallpox is the only disease we've ever completely wiped out, and we're keeping it alive in freezers. Every day those samples exist is a day humans risk the return of one of our worst killers. 1918 Spanish flu. The 1918 Spanish flu killed around 50 million people worldwide. More than World War I, it infected 1/3 of all people on Earth and had unusual features. Instead of mainly killing very young children and very old people like typical flu, it killed healthy young adults at high rates. The virus disappeared after the pandemic ended, and for decades it was just a scary part of history. Then, in 2005, scientists did something controversial. They brought it back. Researchers from the CDC and other institutions rebuilt the 1918 flu virus from genetic material recovered from victims' bodies, some preserved in Alaskan permafrost, others in tissue samples. They published the complete genetic sequence and successfully created a living version of the virus. The stated purpose was research. Understanding what made the 1918 flu so deadly could help prepare for future pandemics. The rebuilt 1918 flu is stored at the CDC in Atlanta in BSL-3 enhanced and BSL-4 facilities. Experiments with the virus showed it was extremely deadly. When tested on mice, the 1918 flu killed 100% of infected animals. When tested on monkeys, it caused rapid and severe illness. The virus copies itself faster and spreads more efficiently than modern seasonal flu strains. Many scientists questioned whether rebuilding this virus was wise. In 2005, articles in major science journals asked, "Is this really a good idea?" The concern was twofold. First, the rebuilding showed that creating deadly viruses from published genetic sequences was possible, potentially providing instructions for biology. Second, it created a sample of an extinct civilization-ending disease that now exists in a lab and could potentially escape. The 1918 flu is especially dangerous because it's a completely new strain. While seasonal flu spreads constantly and people have partial protection from previous infections and vaccines, the 1918 strain is completely new to modern immune systems. If released, it would behave like a pandemic flu, spreading rapidly through an unprotected population. Modern medicine would help. We have better treatments, ventilators, antibiotics for secondary infections, and could potentially develop vaccines. But the 1918 flu spread incredibly fast. It went from the first cases in March 1918 to worldwide pandemic by fall. With modern airplane travel, it would spread even faster today. Before vaccines could be made and distributed, millions could die. The rebuilding of the 1918 flu set an example. If scientists could rebuild one extinct pandemic virus, they could rebuild others. In 2017, researchers published a paper showing how to create horsepox, a relative of smallpox, using mail-order DNA in about $100,000. The message was clear. The technology exists to rebuild any virus whose genome has been sequenced and published. The 1918 flu exists in labs right now because scientists made a deliberate decision to bring it back. It was extinct. We were safe from it, and then we brought it back for research. The samples are stored under high security, but they exist, and unlike naturally spreading germs, this virus has no right to exist. We chose to make it real again. Ebola Zaire. Ebola Zaire is the deadliest type of Ebola virus, with 60% to 90% of infected people dying, depending on the outbreak and available medical care. The virus causes hemorrhagic fever. Victims experience internal and external bleeding, organ failure, and often die within days of showing symptoms. It's a horrible way to die, and Ebola outbreaks terrorize affected communities. The 201 for 2016 West Africa Ebola outbreak killed over 11,000 people and showed how devastating Ebola could be when it reached city areas. Previous outbreaks had been stopped partly because they happened in remote villages. But in 2014, Ebola reached cities with international airports. Cases appeared in the United States and Europe when infected travelers arrived from West Africa. The outbreak caused global panic and required massive international help to stop. Ebola Zaire samples are stored at BSL-4 facilities around the world, including the CDC in Atlanta, U.S. Army Medical Research Institute of Infectious Diseases at Fort Detrick in Maryland, the National Institutes of Health, Public Health England, and other facilities in Canada, Germany, France, and elsewhere. These labs study Ebola to develop vaccines and treatments. Research on Ebola has led to important breakthroughs. The RV's Visibo vaccine, developed through research using live Ebola virus, proved effective during the 201 for 2016 outbreak and has been used in later outbreaks. Treatments like monoclonal antibodies have also been developed through research using live virus. This is the argument for keeping Ebola in labs. We needed to develop ways to fight it. But Ebola in labs creates dangers. In 2004, a Russian scientist working at Vector died after accidentally sticking herself with a needle containing Ebola. She developed hemorrhagic fever and died despite treatment. Her death showed that even in maximum security labs with trained workers, accidents happen. If Ebola escaped from a lab into a major city, the results could be catastrophic. While Ebola requires direct contact with body fluids, it doesn't spread through air like flu. It spreads quickly when people care for sick family members or during burial practices. In hospital settings without proper protective equipment, healthcare workers get infected at high rates, as happened in West Africa. The virus is extremely deadly. Even with modern intensive care, death rates are high. During the 2014 outbreak, patients treated in advanced medical facilities in the US and Europe had better survival rates but still faced 30 to 40% death rates. In places with limited resources, death rates exceeded 70%. If Ebola spread in a major city before containment measures were put in place, thousands could die. What makes Ebola especially it's the possibility of mutations. Current Ebola strains spread through direct contact, but viruses change. In lab experiments, researchers have made Ebola more easily spread in animals. A 2012 study showed that Ebola could spread through breathing drops between pigs and primates under laboratory conditions. If a mutation made Ebola airborne in humans, it would be apocalyptic in airborne virus with 70% plus death rates. Ebola exists in multiple labs, each a potential point of failure. More facilities mean more risk, and research on Ebola sometimes involves changing the virus, making it more easily spread or more deadly in animals to study how diseases work. These experiments create risks that the modified viruses could escape. Marburg virus. Marburg virus is Ebola's equally deadly cousin. Like Ebola, it causes hemorrhagic fever with death rates ranging from 23% to 90%, depending on the outbreak. The virus first appeared in 1967 when laboratory workers in Marburg, Germany, hence the name, and Belgrade, Yugoslavia, but became infected while working with tissues from African green monkeys imported from Uganda. 7 people died in that outbreak. Since then, Marburg has caused occasional outbreaks in Africa. most notably a 2004-2005 outbreak in Angola that killed 90% of infected people, the highest death rate ever recorded for any hemorrhagic fever outbreak. Most victims died within days of showing symptoms. The virus spread through hospitals and families caring for the sick. Marburg samples are stored at the same BSL-4 facilities that store Ebola, the CDC, USAMRIID, NIH, and several international research centers. The virus is studied for vaccine development and to understand hemorrhagic fever disease processes. Research has produced experimental vaccines that show promise in animal studies, but no approved human vaccine exists yet. The security concerns with Marburg are similar to Ebola, but with an additional worry. Marburg has been weaponized. During the Cold War, the Soviet Union's biological weapons program, Biopreparate, weaponized Marburg virus. They produced it in large quantities and developed delivery systems. After the Soviet Union collapsed, information about the program was revealed, raising concerns about whether all samples were destroyed or if some might have ended up in unauthorized hands. Ken Alibek, someone who left the Soviet bioweapons program, wrote in his book Biohazard that the Soviets had successfully weaponized Marburg in tested delivery systems. The program was officially ended in the early 1990s, and facilities were supposed to be taken apart, but questions remain about whether all dangerous materials were accounted for. If Marburg escaped from a modern research facility, the outbreak would mirror Ebola: rapid spread through direct contact, high death rates, terror in affected communities, and potential for international spread through airplane travel. The 90% death rate seen in the Angola outbreak makes Marburg potentially even more deadly than most Ebola strains. The virus's history as a bioweapon makes it especially concerning. The Soviets chose Marburg for weaponization partly because of its extreme deadliness and partly because no vaccine or treatment existed. Even today, treatment is supportive care only. There's no specific antiviral drug. A deliberate release would be devastating. Marburg is also concerning because it occasionally emerges naturally. The virus's natural home is the Egyptian fruit bat, and people can become infected through contact with bats or caves where bats live. This means new outbreaks can occur, providing opportunities for the virus to change or adapt. Studying the virus in labs is important for pandemic preparedness, but it also means keeping one of the world's deadliest germs in storage where accidents could happen. Nipah virus. Nipah virus emerged in Malaysia in 1998, causing an outbreak that killed 105 people and led to the killing of over 1 million pigs. The virus jumped from fruit bats to pigs to humans. Infected people developed encephalitis, brain inflammation, with death rates of 40% to 75%. There is no vaccine and no specific treatment. Since the initial outbreak, Nipah has caused regular outbreaks in Bangladesh and India. These outbreaks are terrifying. The virus spreads from person to person, has high death rates, and survivors often suffer permanent brain damage. The 2018 outbreak in Kerala, India, killed 17 of 19 infected people, a 90% death rate. What makes Nipah especially concerning is its pandemic potential. Studies have shown that the virus can spread through breathing drops, meaning it could potentially cause an airborne pandemic. During outbreaks in Bangladesh, person-to-person transmission occurred, including transmission from patients to healthcare workers. The virus can also spread through contaminated food, particularly date palm sap contaminated by infected bats. Nipah samples are stored at multiple BSL-4 facilities, including the CDC, CSIRO, Australian Animal Health Laboratory, and several research centers in Asia. Scientists study the virus to develop vaccines and treatments and to understand how it spreads. In 2011, the film Contagion used a fake virus based on Nipah as its pandemic germ, highlighting the virus's pandemic potential. The film's scientific advisors chose Nipah-like characteristics because they represented a realistic worst-case scenario: high death rates, breathing transmission, rapid spread, no vaccine or treatment. Research on Nipah has shown disturbing findings. Studies show that the virus can infect a wide range of mammals and can sometimes spread through the air between animals. In 2012, researchers showed that ferrets, often used as models for human breathing diseases, could transmit Nipah through breathing drops. This raised concerns that the virus might be capable of efficient human-to-human, airborne transmission if certain changes occurred. If Nipah escaped from a lab, especially a strain that had been made more easily spread through research, the results could be catastrophic. An airborne virus with 50 to 90% death rates would cause global panic. Unlike Ebola, which requires direct contact with body fluids, an airborne Nipah virus would spread like flu, potentially reaching every country within weeks. The virus's natural emergence pattern, jumping from bats to intermediate hosts to humans, means new outbreaks will occur naturally, but the lab-stored samples represent concentrated risk. They're studied specifically because they're so dangerous, and that danger is what makes their storage so concerning. Lassa fever virus. Lassa fever is common in West Africa, causing an estimated 100,000 to 300,000 infections and 5,000 deaths every year. Most cases are mild or have no symptoms, but severe cases involve hemorrhagic symptoms, organ failure, and death. The death rate in severe cases is about 15 to 20%, but can be much higher in certain populations, especially pregnant women. Death rates above 80% in the third trimester. The virus is spread mainly through contact with the urine or feces of infected mastomys rats, which are common in West African homes. Person-to-person transmission occurs through direct contact with infected body fluids. Healthcare workers are at high risk, and nosocomial hospital-acquired outbreaks are common in West Africa. Lassa fever samples are stored at BSL-4 facilities, including the CDC, Yosemite Bernhard Note Institute in Germany, and several African research centers. Research focuses on vaccine development. Several promising candidates are being developed and improving diagnostic tests and treatments. What makes Lassa concerning as a pandemic threat is its prevalence and potential for spread. Unlike rare viruses like Ebola or Marburg that cause occasional outbreaks, Lassa infects hundreds of thousands of people every year. This means the virus has constant opportunities to change and adapt. If change is increased, how easily it spreads or its deadliness. A local West African disease could become a global threat. Cases have been sent internationally. Travelers returning from West Africa have brought Lassa to the United States, United Kingdom, Germany, and other countries. Most imported cases have been contained, but they show that the virus can reach anywhere through airplane travel. In 2020, Germany experienced a Lassa fever scare when a medical student who had volunteered in West Africa returned home and died from the disease. Several healthcare workers who treated the patient were exposed and monitored. The incident showed how easily hemorrhagic fever viruses can spread internationally, and how difficult they are to contain even in advanced healthcare systems. Research on Lassa virus has involved controversial experiments. Scientists have studied how the virus might become more easily spread and what genetic changes would make it deadlier. While this research aims to predict and prevent pandemic strains, it also creates those very strains in the lab. If these modified viruses escaped, they could be more dangerous than naturally circulating Lassa strains. The large number of facilities storing Lassa increases the risk. Because the virus is common in West Africa and relatively common compared to Ebola or Marburg, more labs keep samples for research. Each facility is a potential point of release. And because Lassa causes milder symptoms in many people, someone infected in a lab accident might not realize they were sick until they had already exposed others. Engineered H5N1 bird flu. In 2011, two research teams did something that sparked international controversy. They engineered H5N1 avian influenza to spread between mammals through breathing drops. Natural H5N1 doesn't spread easily between humans. It mainly infects birds, and humans get infected through close contact with infected poultry. But the engineered strains could spread through the air between ferrets, the animal model for human flu, meaning they could potentially cause an airborne human pandemic. The research was done by teams led by Ron Faucier in the Netherlands and Yoshihiro Kawaoka in Wisconsin. Both teams made genetic changes to H5N1, creating strains that could spread through breathing drops. When they tried to publish their findings, the US government initially tried to prevent publication, arguing that the research was essentially creating a bioweapon and publishing a recipe that terrorists could follow. After much debate, the papers were eventually published in 2012, though with some details left out. The researchers argued that the work was important to understand how pandemic flu strains emerge and to prepare systems to detect dangerous changes in nature before they cause pandemics. Here's why this is terrifying. H5N1 has a 50 to 60% death rate in humans. Most flu pandemics have death rates of 0.1% to 2%. The 1918 Spanish flu, which killed 50 to 100 million people, had a death rate around 2 to 3%. An airborne flu virus with 50% death rate would be apocalyptic. If the engineered H5N1 escaped from a lab and spread like seasonal flu, it could kill billions of people. The engineered strains are stored at the labs where they were created. Erasmus MC in Rotterdam and the University of Wisconsin-Madison, as well as possibly at other facilities they've been shared with for research. They're kept under BSL-3 enhanced conditions, which is high security, but notably one level below BSL-4. The controversy over this research has never fully died down. In 2014, after several high-profile lab accidents involving anthrax and smallpox at U.S. government facilities, the Obama administration put in place a stop on gain-of-function research experiments that make germs more dangerous. The stop specifically covered research that could make influenza, MERS, and SARS viruses more easily spread or deadly. The stop was lifted in 2017 under new guidelines, and gain-of-function research resumed. The debate continues. Is this research reckless, creating pandemic germs that wouldn't exist in nature? Or is it necessary to understand and prepare for naturally emerging pandemic threats? Meanwhile, the engineered H5N1 strains exist. They're stored in freezers. They've been shared between research labs. Every facility that has samples is a potential point of release. And unlike natural H5N1, which doesn't spread easily between humans, these strains were specifically engineered to do exactly that. Original SARS, The original SARS, the original SARS, acute respiratory syndrome coronavirus, emerged in 2003, causing a pandemic that infected over 8,000 people and killed 774. The virus spread internationally, reaching 29 countries before being stopped through aggressive public health measures. SARS had a death rate around 10%, much higher than seasonal flu or even COVID-19. After the pandemic was stopped, SARS disappeared from nature. The last human case was in 2004. Like smallpox before it, SARS was eliminated not through vaccines, but through old-fashioned quarantine and isolation. And like smallpox, we kept it. Samples of SARS-CoV are stored at multiple BSL-3 and BSL-4 facilities worldwide. Here's where things get concerning. After SARS was eliminated from nature, there were multiple lab escapes. In 2003-2004, there were 4 separate incidents where SARS escaped from labs. In Singapore, a graduate student became infected through a lab accident and spread the virus to others before being quarantined. In Taiwan, a SARS researcher became infected in December 2003, potentially exposing 74 people on an airplane. In Beijing, China, in April 2004, 2 researchers became infected in a lab studying SARS. They spread the virus to others, causing a small outbreak. 1 person died. The outbreak included a 20-year-old nurse who had no connection to the lab. Pure secondary transmission from a lab escape. These weren't theoretical risks. SARS actually escaped from labs multiple times after it was eliminated from nature. The virus that no longer existed in the wild was brought back through lab accidents. SARS samples are stored at facilities including the CDC, various Chinese research institutes, Canadian labs, and European research centers. The reason is research, developing vaccines and treatments in case SARS comes back, and studying coronavirus biology to prepare for future pandemics. After COVID-19, research on SARS-CoV has increased because understanding the original SARS helps understand SARS-CoV-2. But SARS-CoV is uniquely concerning because we know it escapes from labs. It has a documented history of doing exactly what we fear, getting out of containment and causing outbreaks. Each facility storing SARS is a potential source of a new SARS pandemic. Moreover, research on SARS has included gain-of-function experiments. Scientists have created chimeric SARS viruses, combining parts of SARS with parts of other coronaviruses to study how different virus parts affect how easily it spreads and its deadliness. Some of this research has created viruses that don't exist in nature and are potentially more dangerous than the original SARS, the COVID-19. The pandemic has sparked intense debate about the origins of SARS-CoV-2. While most scientists believe it emerged naturally, the lab leak theory that SARS-CoV-2 accidentally escaped from a research facility has received serious consideration. Whether or not COVID-19 came from a lab, the debate has highlighted that coronaviruses are studied extensively in labs, and those labs are potential sources of outbreaks. SARS-CoV samples exist in freezers around the world right now. The virus that naturally went extinct is being kept alive artificially for research, and we know from documented history that it can escape. Every day those samples exist is a day we risk bringing back a disease we already eliminated once. Monkeypox. Monkeypox became globally notorious in 2022 when it spread internationally, causing the largest monkeypox outbreak ever recorded outside Africa. The virus is a relative of smallpox, though usually much less deadly. However, monkeypox research in labs has involved creating more deadly strains and studying how closely related pox viruses can be changed. The concerning part isn't monkeypox itself, it's the research being done on pox viruses in general. Multiple labs study orthopox virusi as a family, including smallpox, monkeypox, cowpox, and others, to understand how these viruses work and to develop broad-spectrum treatments. This research sometimes involves creating hybrid or modified pox viruses. In 2017, researchers showed that they could create horsepox virus from scratch using mail-order DNA pieces and published genetic sequences. Horsepox is closely related to smallpox. The researchers argued this was important to show that smallpox could potentially be recreated by terrorists or bad nations. Therefore, we need better defenses. Critics argued they'd just published a recipe for but the same techniques used to create horsepox could theoretically be used to create smallpox or to create hybrid pox viruses, combining the easy spread of one strain with the deadliness of another. Research has also explored what genetic changes would make pox viruses more deadly or more resistant to vaccines. Samples of various orthopox viruses are stored at BSL-3 and BSL-4 facilities worldwide. Research increased after the 2022 monkeypox outbreak, with scientists studying why this outbreak spread so differently from previous outbreaks. Some research involves changing monkeypox to understand how it spreads, essentially making it more easily spread in lab animals to study how transmission works. The risk is that research meant to understand pox viruses could create new dangerous versions. a modified monkeypox strain that combined easy human-to-human transmission with smallpox-level deadliness would be catastrophic, and the 2017 horsepox creation showed that the technology exists to create pox viruses from scratch, meaning even if all samples were destroyed, the information exists to recreate them. Monkeypox itself has a relatively low death rate, 1 to 10%, depending on the strain and access to healthcare, but it's painful, disfiguring, and can cause severe problems. A more deadly strain escaping from a lab could cause a pandemic worse than the 2022 outbreak, and research creating more dangerous strains event. For legitimate scientific purposes, creates samples that shouldn't exist, reconstructed extinct pathogens, beyond the specific viruses already mentioned. There's a broader category of concern, extinct germs that have been or could be rebuilt. Scientists have developed the ability to rebuild viruses from historical tissue, samples, or even just from published genetic sequences. This means viruses that disappeared from nature either through eradication or natural extinction can be brought back. The 1918 flu rebuilding proved this was possible, but other extinct germs could be rebuilt. Ancient diseases preserved in permafrost or ice cores, including viruses that infected humans thousands of years ago. Historical pathogens like medieval plague strains, which have been partially rebuilt from DNA taken from plague victims' teeth. Extinct animal viruses that could potentially jump to humans if rebuilt. Research facilities studying ancient DNA and paleomicrobiology are rebuilding genetic sequences from extinct microorganisms. While most of this research focuses on bacteria and doesn't involve creating live germs, the ability exists to create live viruses from ancient genetic material. In 2016, researchers rebuilt a 30,000-year-old virus from Siberian permafrost. They revived the virus, which infected amoebas, not humans, and showed it was still infectious. This showed that ancient viruses can remain alive or be rebuilt even after thousands of years. As climate change melts permafrost, there are concerns that ancient germs could be released naturally, but labs are also deliberately finding and studying these germs. The big question is, should we be bringing back extinct viruses at all? These germs went extinct for a reason. Either we eliminated them, or they died out naturally. Rebuilding them creates dangers that didn't previously exist. Every rebuilt virus is stored in a lab, creating a potential point of release. Some of these rebuilt germs exist at facilities including the CDC, NIH, various universities, and international research centers. The reason is always research, understanding disease history, preparing for similar germs, developing broad-spectrum treatments. But each rebuilding is a Jurassic Park moment. Just because we can bring something back doesn't mean we should.
These 10 viruses and virus categories represent some of the most dangerous germs stored in laboratories worldwide. They exist in freezers, secured behind multiple containment barriers, monitored by security systems, accessible only to authorized people. They are kept for legitimate reasons: research, vaccine development, public health preparedness. But they represent an existential risk. The basic question is whether the benefits of keeping these germs justify the dangers. Supporters argue that we need to study deadly viruses to develop ways to fight them. How can we create vaccines without samples of the virus? How can we prepare for future outbreaks without understanding past pandemics? How can we defend against bioterrorism without studying potential bioweapons? Critics argue that the dangers are too high. Every facility storing these germs is a potential source of release. Lab accidents happen. We've documented escapes of SARS, anthrax, smallpox scares, and many other incidents. Security can be broken. Employees can become angry. Natural disasters can damage buildings. Human error is inevitable given enough time and enough facilities. The COVID-19 pandemic, regardless of where it came from, showed how devastating a breathing virus can be, even with relatively low death rates, around 1%. Now imagine a virus with 50% death rate like H5N1, or 70% death rate like Ebola, or 90% death rate like Marburg in some outbreaks. Imagine these viruses spreading with the efficiency of flu or SARS-CoV-2. The death toll could be in the billions. Some of these viruses, smallpox, SARS, the 1918 flu, were extinct or eliminated. They didn't exist in nature. We chose to keep them or bring them back. That choice creates ongoing risk. Other viruses, Ebola, Lassa, Nipah, exist in nature and will cause outbreaks regardless of whether we store them in labs. But concentrating them in high-security facilities creates the risk of larger releases than would happen naturally. The engineered viruses, modified H5N1, hybrid pox viruses, rebuilt extinct germs, are especially concerning because they wouldn't exist without deliberate human creation. These are viruses designed to be more easily spread or more deadly than natural strains. They exist only because scientists created them for research. If they escape, we'll have caused the very pandemic we were trying to prevent. Rules for these facilities are inconsistent internationally. While the US, Europe, and other developed regions have strict biosafety rules, enforcement varies. Facilities in some countries operate with less supervision. The more facilities storing these germs, and the more varied the security standards, the higher the total risk. They have been caused to destroy all remaining smallpox samples for decades. The WHO has voted on the issue many times, and each time the decision has been to delay destruction. Similar debates exist around SARS samples and other eliminated germs. The research community generally opposes destruction, arguing we might need the samples in the future. But might need is weighed against might cause a pandemic. The COVID-19 pandemic should be a wake-up call about lab biosafety. Whether or not SARS-CoV-2 came from a lab, the pandemic showed how unprepared the world is for a serious outbreak. Now consider that labs around the world are storing viruses far deadlier than COVID-19, and sometimes creating new, more dangerous strains for research. Some experts have proposed alternatives to storing live germs. Instead of keeping virus samples, labs could store just genetic sequences. Modern biology allows creating viruses from genetic sequences relatively quickly if samples are truly needed. This would eliminate the risk of accidental release while keeping the ability to work with viruses if necessary. But this approach has its own dangers. It might make it easier for bad people to create bioweapons from published sequences. Others have proposed reducing the number of facilities storing the most dangerous germs. If only 1 or 2 maximum security facilities worldwide stored smallpox instead of 2, the risk would be cut in half. If only a handful of facilities stored Ebola instead of dozens, the total risk decreases. But centralization creates other problems. If those few facilities have problems, the entire world's research ability is affected. The uncomfortable truth is that there are no perfect answers. Storing these viruses creates dangers. Destroying them eliminates research abilities that might be needed. Reducing the number of storage sites concentrates risk, but also makes security easier. Publishing research helps the global scientific community, but also provides information to potential bad people. What's certain is that right now, today, civilization-ending viruses are stored in labs around the world. They exist in amounts big enough to cause pandemics. They are secured by human systems that will inevitably fail given enough time. Some of them have already escaped from labs in the past. And research continues to create new, potentially more dangerous strains. Every day those viruses remain in storage is a day we accept the risk that they might escape. Every new facility that stores them increases the total risk. Every gain-of-function experiment that makes germs more dangerous creates something that shouldn't exist. The question isn't whether a lab release will happen. The question is when, and whether we'll be prepared for it when it does.